All right. Next would be section 6, magnetic forces on moving charged particles, but we are skipping section 6. Okay? So we're just going to skip it. 36.7 is magnetic forces on current carrying wires. So we talked about how an electromagnet makes a magnet. Now, if we had this coil hanging from a wire, just sitting by itself, could we take another magnet and push this around? Well, yeah. I mean, this is just a magnetic field in here, so we could put up a magnet to it, attract it at one end, or push it away with the other end. The same thing with this wire. If this is a magnetic field, if you took a big magnet next to this wire, now that magnet is going to exert a force on this wire. That magnet is going to exert a force on the current carrying wire. Does that make sense? All right, here we go. If the particles are inside a wire, whoops, the wire will also move. It seems like it's starting in the middle of something. Let's go to a video. All right. All right. All right. Here we go into section 36.7. Magnetic forces on current carrying wires. So, we already established that a current carrying wire will deflect a magnetic compass. So the wire makes a magnet field that moves a magnetic compass. Just as a current carrying wire will deflect a magnetic compass, a magnet will deflect a current carrying wire. Both cases show different effects of the same phenomena. So if we have a wire right there with a current going through it, going this way, and we bring this magnet up to it, this wire is going to move up. It's going to be pushed away from this magnetic field going from north to south. And then if we switch the direction of the current, it will go the other way. It will get pulled down. A current carrying wire makes a magnetic field. If you bring a magnet near the wire, then the magnet's field will push on the magnetic field of the wire, and then the wire will move. If the direction of current in the wire is reversed, the deflecting force acts in the opposite direction. All right, there's a nice video for this. Let's go find that. All right, so he's got the battery here, and there's hooked up to a wire that then goes across this copper pipe, which is just copper, so it's going to carry the current. And what he's saying is that when he puts the current through here, this wire is going to get deflected. Which way is it going to get pushed? It gets pushed in when he's got the current going this way. So he takes it off, and now he switches the current, and it goes the other way, and now it gets pushed out. So now it's getting pushed out just by the current going through that wire. This big magnet pushes that out. And that's literally magnetism in action. This magnet is pushing the wire that has current going through it. Pretty cool. Okay, back to the slides. The force is maximum when the current is perpendicular to the magnetic field lines. So the magnetic field lines are going from the north into the south, and this current is going perpendicular. So these lines, the magnetic lines are going that way, and the wire is going literally 90 degrees against it. The direction of force is along neither the magnetic field lines nor the direction of current. So the current is going this way, the field lines are going that way, and the force is going up. Oops, up. The force is perpendicular to both field lines and current, and it is a sideways force. So we need all three dimensions to keep track of this. The magnetic field lines are going one way, the current's going another way, and the force is going the third way. The discovery that magnet exerts a force on a current-carrying wire created much excitement. People began harnessing this force for useful purposes, electric meters and electric motors. All right, think about this. What law of physics tells you that if a current-carrying wire produces a force on a magnet must produce a force on a current-carrying wire? So you have a force going from one to the other, and therefore you have an equal and opposite force going the other way. Newton's third law, which applies to all forces in nature. It tells you that forces come in pairs, and they are equal and opposite in direction. So, this section, how is current affected by a magnetic field? It gets pushed around. If you don't understand that at all, then you need to go back and rewatch section 7. Now we are going to go on to section 8, which is the culmination of all of this. We start with a meter, and then we build a motor. The principal difference between a galvanometer, a meter, and an electric motor is, in an electric motor, the current is made to change direction every time the coil makes a half a revolution, or a half a turn. If you don't understand that, don't worry, that's what we're going to explain in this section. Here we go. The simplest meter to detect electric current consists of a magnetic needle on a pivot at the center of loops of insulated wire, which is this picture down here. When an electric current passes through the coil, each loop produces its own effect on the needle, so a very small current can be detected. A sensitive current indicating instrument is called a galvanometer. So let's look at that. Let me read this first, then we'll go to the pictures. A more common design employs more loops of wire and is therefore more sensitive. The coil is mounted for movement and the magnet is held stationary. The coil turns against a spring, so the greater the current in its loops, the greater its deflection. So I don't need you to understand how this works. But here I've got a magnet around it, and there's a loop of wire, loops of wire, and this is on a pin that can rotate, so this cylinder can swing around. So when you put current through those wires, through the coils, you're going to make a field, and that field is going to interact with the permanent magnet. The more current, the more the field bends, and the more the needle moves. Does that make sense? Great. A galvanometer may be calibrated to measure current, in which case it's called an ammeter, or it may be calibrated to measure voltage, in which case it's called a voltmeter. Now, if we were in class, I would already have you using ammeters and voltmeters, but we aren't. So you use those in the PhET labs. All right, so I want to keep this simple. So I explained how the coil, you have current go through the coil and it deflects this needle. So now the same thing is here. We've got current coming through here, and you see how it connects to this, and it goes through this loop this way, and then this loop around, and then back to the battery. So you've got current going this way on that side of the wire, and the opposite side on this side of the wire. So what's going to happen is it's going to bring this side is going to come up, and this side is going to go down until they're perfectly flat. And the magnetic field in the middle of this hole is going in line with that magnet. So you could get this to turn until it's flat. But then what happens in an electric motor is you switch the battery so that the current goes the other way. And now if you switch the current, well, since this was already moving up, it's going to keep moving up, and it's going to swing around and point the other half. And then you switch it back, and it makes a half turn, and you switch the wires, and it makes a half turn, and you switch the wires, and it makes a half turn. Well, do you see how these wires are connected to this piece of metal, and this the arm of that wire just slides around the outside? Well, that's the trick of how it works. It's in one connecting to one half of the battery and then the other half of the battery. So what ends up happening is as this is rotating, this is switching back and forth. So the current's going one way when it needs to go, and then it switches to the other side. The current is reversed during each half revolution by means of stationary contacts on the shaft. That's the shaft, and those are the stationary contacts. The parts of the wire that brush against these contacts are called brushes. The current in the loop alternates so that the forces in the upper and lower regions do not change directions as the loop rotates. So the current is alternating, and then the forces do not change direction. It keeps the loop rotating. The rotation is continuous as long as current is supplied. Large motors, don't need to worry about. No, this is not the question I want to ask. What I want to ask is, how does an electric motor work? And let's go to the video. All right, so this guy's, let me pause it. He's got a motor in here, a DC motor, and there's the magnet that's helping it, that push it, that's working. I'm sorry. This is just an example. He's got a DC motor, he's putting up current, and the more current he puts up in there, the faster the motor goes. You can see the motor sparking. All right, now we're going to go to the computer animation. It's going to rotate around. All right, pause it there. There's the battery, a switch shuts it, and the current comes in the top and out the bottom. Now, while this part, that's called the commutator, that part of the ring is in contact with this coil, the copper wire loop, then the current is going this way. And while it's going that way, it shuts. It rotates down. And then when it gets down to, down to here, where it would be flat, it skips over, and now this side goes, and the current switches direction. So now this was moving up, and normally it would just stop if we didn't switch the current, but we switch the current, and that goes up and flips to this half. Then we switch the current again, and it goes to the other half. And that's what I mean when I say the coil will point halfway around, and then you flip it, and it goes to the other side. So here are the basics. There's the positive and the negative side they showed you. And so the current's coming out of the screen, and that pushes the current carrying wire to the right. And so it's getting pushed away from this side, and it's getting pulled towards that side, the attraction. So that's why the current carrying wire moves this way in the magnetic field from this magnet. So this current carrying wire is going to move halfway, and when it gets down here, it switches the current over, and now this is being pulled this way. It switches, and now it's getting pulled over to this side, and it switches. Now remember, the other way to look at it is the magnetic field is in the middle of the loop. So right here, the magnetic field is pointing up, and it's with the way the magnet goes. So when you switch the way the magnet's going, now it's pointing the other way. So now this side wants to come around and get drawn to the red side, the north side of the magnet. All right, back to the oh, and that is it. That's how the motor works. All right, we're going to call that done for the day. We'll check in again and talk about how the motors work on Tuesday when we're back in class. And I'm going to see if I can get into the building and use my own model to make the explanation better.